small venture-backed company based in Cambridge, Massachusetts. MC10 is about reshaping electronics. So many of the talks you've seen here this morning have to do with the infrastructure around it, clinical care and so forth, information exchange, transfer into the cloud and so forth. MC10 is focusing on the piece of that where the data is gathered, and that's on the body or in the body, as we'll show you. So as a tech executive, as you might expect, I'm a rabid early adopter of technology. I buy all sorts of interesting gadgets, some of which get used, some of which don't. Many of which we actually end up tearing apart. So my kids and I occasionally will have a take it apart day where we rip things apart, and this is basically what you'll find in most of the devices that you carry around, your laptops, your phones, other devices that you might have on you or carry with you every day. Those are printed circuit boards, those are integrated circuits, and all of these devices are housed in typically metal or plastic housings. They end up being fairly large, fairly rigid, and bulky. We're forced to adapt to them, usually not the other way around. The evolution of electronics is meant, of course, with Moore's law, which is the doubling of transistors, which is the doubling of, roughly the doubling of processing speed, means that we have the ability to put more and more functionality into a smaller and smaller space. So here you can see a 15, 20-year span of cell phones whose functions and horsepower, the underlying computation that's possible within the devices, increasing dramatically, exponentially in many cases. But what happens when you look at patient care? The same types of electronics that are outside the body are still improving rapidly, but the devices on the body are not improving as rapidly. So in this case, a premature baby with electrodes and monitors and wires and so forth is sort of forced to live with that, those electronics in those forms. Similarly, even in the elderly populations where we have many of the devices that were talked about here today, they have to plug into them. They have cuffs, they have wires, bulky devices that might sit in their home. All of these are large, bulky, and rigid. But what if we could change that paradigm? What if we could change the electronics themselves to be conformal, put them on the body, have them communicate with external devices such as smartphones, and then move into the cloud, just as previous speakers have alluded to. And so we're soft and curvy. Electronics are rigid, and the mismatch of the modulus of these materials prevents that from easily happening. But what we'd like to be able to do, though, is take electronics and match them to the underlying tissue. And again, whether that tissue's inside the body, whether you want to have a cardiac device, or on the body, a device mounted directly to the skin. And so these are the types of devices that we're building and using right now. This is a functioning device that can actually measure ECG, EMG. We have strain gauges that can measure the flexing and motion of the underlying skin. We have wireless power that can actually inductively couple to the device to read data, very similar to what you might have seen in RFID devices that can interrogate a device, simultaneously powering it and extracting data from it. But what we'd like to do, of course, is do this continuously, as has been spoken about here many, many times. And so these types of devices, we're trying to take electronics and take them from the 2x4 stage to the tissue paper stage, where in fact you can thin them, embed them, and interconnect them in such a way that they become very conformal, very flexible, and in fact match the modulus of skin. And so these rather alien-looking structures and architectures allow us to do that. Based initially on the work of John Rogers out at University of Illinois, we're able to take silicon materials and interconnects and make them stretchable and bendable, almost spring-like devices. At its most fundamental, the idea is simple. If you make things thin enough, they'll bend, they'll flex, even stretch if you make them in the right geometries. And so we can take these types of devices and do that with them. And so you end up with interconnected islands of devices, silicon devices that are the processing chips, the communication chips, thin film batteries, and so forth, all of which we can now get into systems that are on the order of maybe a couple of 100 microns, where 100 microns is the thickness of a piece of paper. We can get them even thinner than that, and we've been working on that as well. And so we have these conformal systems that can sit on polymer materials and be encapsulated and protected. So you end up with something on the body that's more akin to a Band-Aid rather than strapping an iPhone to your body. And so these types of devices, in fact, I'm wearing one, I'll show you, on my arm. I wear this quite often. I put this on just a couple of days ago. But this device I can wear usually for about 7 or 8 days. After that, it starts to peel off like a Band-Aid would after that period of time. So it goes through a series of when I work out or exercise, ride my bike, when I shower, and so forth, and the device can stay on. So that's a property of the materials, the adhesives, the encapsulants, and the polymers that are used to hold the electronics. The electronics themselves are typically not exposed directly to the environment, but are protected by that layer, as well as the epidermis underneath. And so with these types of devices, we can do quite a few interesting things. But I think one of the points that was brought out here today multiple times was moving from discrete events to episodic events, or these episodic instances where you're visiting a clinician for very brief periods a few times a year to continuous monitoring. So moving from that discrete model to a continuous model makes a huge difference. We've seen evidence of that here today. So this seamless sensing as well also makes it transparent to the user and invisible to the user. I do not notice this when it's on my body at all. We have a variety of different patches and styles that we've tried, and typically you just don't notice them. After you put them on, then you go about your business during the day. It's not a large pendant, it's not a large device that's strapped to your body. It becomes quite seamless. But of course you have to put this in the context of the greater information exchange that's happening and be able to take that data, turn it into information, do something interesting with it, chart it, trend it, do regression on it, and be able to make decisions, diagnoses based on that information. And so by having a complete system where you're doing the analysis, where you're moving data into the cloud so that other clinicians can look at that data, make assessments of their own, and make a prescription of some kind. And that's all very easily made possible by having thin conformal devices directly on the body. And so a fever patch for a baby is one example of a system that we've been looking at. These are devices where you can measure the temperature and log the data. You can have local communication either through NFC, which is found on most Android phones today, or Bluetooth, which is found on almost every smartphone today, or Bluetooth LE, the new generation low-power Bluetooth. We also are looking at and doing quite a bit of work in cardiac applications, where we're taking devices such as catheters and reinventing them to have electronics at the distal end of these devices. So you go in the femoral artery as usual, up into the pulmonary vein. You can then do mapping. You can do treatment and ablation based on that mapping, so you can look for AFib issues. You can also increase the density of these devices far beyond what we're showing here, where we've created systems with many dozens of electrode points where you can measure biopotentials at such a resolution, you're actually getting imagery, moving pictures of the electrical activity in the heart. We've created epicardial sheets that can go on the surface of the heart and be deployed through minimally invasive techniques directly to the surface and provide essentially a moving picture of what's happening in the electrical occurrence across the heart. You see all sorts of interesting artifacts, rotors and other things, which are thought to be center points that can be tackled during the ablation to treat AFib. And so we have a pretty extraordinary range of devices. Here at Penn with Brian Litt, we've also looked at sheets that go in the brain and do imaging, where Brian's research is looking at targeting epileptic seizures and so forth. By having increasing density of measurements, you move from this discrete model spatially, not temporally necessarily, but this gives you a much higher resolution model of what the brain activity is doing. And so that kind of work is beginning. So on the body, we have a wide variety of things that we can measure today. We're launching our first product with Reebok. It's actually a sports-related product, resulting in a device that can detect impact to the head. This is related to contact sports, concussion, and traumatic brain injury, where we can actually detect forces to the head. We're not diagnosing concussion. It's not a medical device. It's simply measuring impact. And above certain thresholds, it indicates whether or not that impact level, the energy delivered to the head, has exceeded a certain threshold, at which point rules and other things can say, you must come outside. It's a pathway to assessment, not a diagnosis device. So these are some of the things that we're working on and building. We also have contracts with the Army and Navy for a variety of things for monitoring soldiers in the field. The Gates Foundation has funded work in our company for a variety of things related to disease detection and so forth in developing countries. And so this simple biopotential patch has a lot of uses. We're building out a number of systems today. We're working in the clinic at MGH we're working with folks at Sarver Heart Center in Arizona. This can be transformative as to how we do continuous on-the-body and in-the-body based monitoring. And so we continue to do that. MC10 is growing quickly. We're still a small company doing too many things with too few people, but we're growing very quickly and having a lot of fun too.